Today, I had the privilege yet again to speak with Scott Walter, factory robotics and simulation expert, and we'll get into that stuff during the talk. We discussed Google's new robot, how it compares to Optimus, how the future of robotics is going to go, and after the main video, I have bonus video because I kept on recording. There's a super nerdy discussion about robot arms and neural networks. If you're interested in that, stick around after the end. Anyway, let's take a look. Hey y'all, it's Dr. Know-It-All. I am back with Scott Walter, and we are going to talk about a Google and gosh, was it called One Robot? I believe that's the company. They got together and they created, we were actually just debating before we started recording this, who gets to say it, but essentially it looks like a Dyson with an arm stuck on it. It's kind of weird
what
looking.
I said, a cobot on a Roomba.
A cobot on a Roomba, yeah. So no, it's a weird looking thing. I'm going to go ahead and share my screen here.
Yep. Yes, I can.
Okay, cool. So yeah, this is a still frame of the robot, and someplace in here, I believe they have like a kind of well, actually, this is a little bit freaky. This was the part that freaked me out, was when I realized they have like 100 of these. And they're all they all go line up and they plug themselves in and they charge at night. So a little bit weird. But anyway, so it's got like a head, I guess, with some eyes. It's also got a LiDAR thing. When you watch the video, you can see the LiDAR spinning in the middle of the body. And then it's got a single arm that it uses to pick things up. Nope, that's OpenAI. Yeah, this guy. So this part right here is the arm. And so it can look around with its little head. This is the LiDAR thing, the little silver thing that looks like a kind of a Coke can size thing. You can see it spinning in the video.
Yeah, you see it spinning around when we go through some of the videos. Yeah.
Right. And then it's got its single
arm.
Oh, yeah,
you can see it better there. You can point out where the LiDAR is.
Yeah, this part right there. And actually, maybe the problem is, of course, this is Cold Fusion, by the way, and I'll put the link to this in the description so you can watch it. I don't want to do too much. This is OpenAI, by the way. This is not Google. Here it is. But hopefully, as it moves out of the way, yeah, you can see the little Coke can size thing spinning. That's the LiDAR system right there. So anyway, that's how it works.
This actually came from Davy Jones' locker. The idea for this.
Okay.
And I don't know what you call a tweet on Teams. I guess it's a Teams post or something like that.
Right.
And I assume you can and just do a share right here. Well, in our eternal Teams channel, my colleague over in the UK, David Jones, just posted this, and evidently he's a Dr. Know-It-All fan, and I didn't know it.
Wow, that's pretty cool. I feel good.
So
I don't know why I'm still not seeing the video or whatever it is yet. It just, there we go. Okay, it just popped up.
Okay. So yeah, so he just sort of thought that maybe you and I should discuss this Cold Fusion video, and of course, anything that DeGogo puts together is definitely worth looking at.
Yeah.
One of the reasons I'm probably considered an insufferable know-it-all is because I've watched too many Cold Fusion videos. So yeah, you can definitely learn a lot from that.
Maybe that's my problem too. I don't know.
Yeah. And I guess what we want to discuss is sort of the two aspects. There's the brain, and then there's the form.
Right.
And sort of the choices they made on the robot itself. Again, sort of the quip I made when I first looked at it is like, oh, they put a cobot on a Roomba. And there's no real kinematic breakthroughs here. As a matter of fact, even the gripper, when we look at it, is a very old school kind of gripper. There's not much to it. Right. So this is not going to be winning any Engelberger Robot Awards for the kinematics. However, you never know.
And it also rolls. It doesn't have legs or anything like that. So I think I wanted to do a comparison eventually, talk about, we have not seen Optimus, but it should be here in a couple of weeks, or at least some version of it. But this is rolling only on the floor, one arm, two finger gripper, all of that kind of stuff. Optimus is obviously much more ambitious in terms of looking like a person.
Exactly. And this is the Cold Fusion video that, of course, you can go to see. And what they do is they talk about the division within Google that makes this. And it's a division called Everyday Robotics. Not everyday astronaut, everyday robotics.
Right, there we go.
And if you go to the website, you will be able to find a lot of things about that. And so, they have some things here which they're sort of showing how it looks like. You can see it's rolling along
Yeah,
there.
there we go. We can see it much better there.
So again, that's why we say it's sort of like they put it on a Roomba or mobile robot platform. And it's a fairly simple or standard kind of cobot. As a matter of fact, it reminds me a lot of the Sawyer arm from Rethink Robotics and a lot of other arms. I can bring that up a little bit later just to kind of look at it. We can see the spinning LiDAR that's on there, and also the camera systems that's up there. Not to throw shade at Google here for coming up with what seems to be a very simple robot. I think the simplicity of that's the whole point.
Right.
They're not trying to waste time on solving the walking problem. Mobility is solved, and they need a robot that's able to be mobile. So they just took a lot of off-the-shelf technologies and put them in there. Same thing with the arm design. And again, even the gripper, I mean, they're not trying to put a fancy arm there. So I think the point is they're like, come up with the most minimalistic robot mechanically, and now put a brain in it. Right. Because if we can't get a brain to get this thing to work, we are not going to get a brain to an AI brain to work in a more complicated one.
Right.
And when you're debugging this, do you really want to be thinking, is the hardware the problem, or is it the AI that's the problem? So you go with like known technologies here. We're trying to push the envelope somewhere else, and that's why it's so simple.
Cool. Yeah, and that's a very good point. I think. And certainly Tesla has given themselves both problems because they have a lot of hardware issues that have not been solved. But yeah, I mean, all of the stuff that you see in this robot are technologies. The physical aspects are technologies that have existed for at least a decade. I don't think there's anything that's brand new or cutting edge looking or anything like that.
Yes, exactly. So I think somewhere in here, like you look at the hand, right there. And that's a very simple gripper, just 2 fingers. They're kind of compliant. It's kind of a big, bulky gripper that they actually mount on the end of the arm. Very standard fare for being able to do that. But there's still a lot of things you can pick up with this.
Right.
There's a lot of tasks that you can perform with it. And if you can't get an AI to do that, then you've got some problems. So exactly. I think they're really trying to cut their teeth the idea of putting some sort of intelligence inside the body of a robot.
Right. And so a very, very different, strategic decision, I guess, than what Tesla did. They're like, we've got cars, we're all in. We think we know how to make these robots and make them walk and talk and do all of that kind of stuff. This robot, I don't believe it even has a voice response system. I think what you do is you tell it what to do, and it just does things. Yeah.
I'm not sure. And it's one arm. It's only one arm.
Right. Right. And one of the examples that DeGogo showed in Cold Fusion was he showed it sorting. You said, sort the recycling into like paper and plastic and metal or something. And so it kind of goes there. Apparently, a lot of this stuff looks like it's in fast motion. Apparently, this is quite a slow machine. So I think that's one issue with it is it's not very rapid in what it does. But the primary thing, as you said, is the software aspect of it. And there are a couple pieces to that. Number one is natural language processing, of course, which is, I think the example is I spilled my orange soda. Please clean it up and bring me, please clean it up and bring me a Coke or something like that. So it has to process a lot of pieces of knowledge to be able to figure that out. Yeah. There we go.
Yeah, exactly. So the idea is to go in and at least start at the source of
Yes.
We never put those in the right bins because we're confused ourselves.
Right. So so you can see that this thing is working. Actually, interestingly enough, did you see the LiDAR was like far lower on that version of the robot? It's interesting. There's different versions of it quite apparently. But so basically you can see it's nothing that it's doing mechanically is outrageously difficult. It's the conceptualization of, oh, that's a piece of plastic that needs to go in the green one, and this is a piece of paper, it needs to go in the blue one, or whatever.
It's doing the labeling just like full self-driving has to do. It has to identify that as a cup, what type of cup it is. Is it a piece of paper? Do I know how to grip it?
Right. Oh, apparently the paper goes in the green bin. So anyway, but so it also, but it's not what they're doing with the gripper, even though it's only 2 fingers, is quite complex because you can see it picking up a plastic cup, and a plastic cup, if you grip it too hard, will crush.
It'll crush, and then you fail. You think you think it's there and your fingers are closing and
Right.
missing it,
Right.
or you go through it trying to get it. So there's all sorts of mistakes that you can make that they're trying to figure out.
Exactly. So there are, I guess it can cook your microwave popcorn for you. So there you go.
Yeah.
A little bit of
Yeah.
a little bit of fun for it. So yeah, you can see that they're kind of like all like set up, and they're charging on 110 volts. So it looked like they were just standard plugs in the wall. So that's cool to see.
Yeah.
So anyway, the fascinating part with this is not so much the mechanical aspects, but the mental, well, whatever you want to call it, the programming / neural network / conceptual issues that it has. So I don't know. I mean, you're much more familiar with robots, but to ask a robot, any of the robots that you're used to playing around with, if you said sort the recycling bin, I don't think it would be able to do that without a whole bunch of hard coding.
Without a vision system. Yeah. So you're
oh, and it doesn't even have a
vision
vision system. Yeah. So you got to see. So,
normal robots do not have a vision system. And they point out in some of the videos, definitely in the cold fusion, that the traditional way that you teach a robot is you physically go through and show it all the different locations, and then it replays that. And I know we've been doing this with a lot of hand waving. If you want to see an example of that, I can kind of show an example of that, and then show how you ramp it up from teaching it every single little instruction to making it more of a task-based thing. Right. And then with the idea that if you start incorporating some sort of vision, maybe you can start to get more and more smarts. So we can attempt to do something like that. Okay. So let's go ahead right here and take a look. So first of all, this arm that we're looking at here, this is the
I like its iPad face.
Yeah, this is the Rethink Robot Sawyer robot. And it's a 7-axis arm, and let's say it's kinematically very similar, but they've made some differences. For instance, this wrist up here, which has a huge offset in Sawyer, they do not. The everyday robot, they slim that down and put that in there. They've also put the elbow kind of the other side for packing it, but the offsets and everything are similar. The main thing about this particular arm is I've talked about this being a 7-axis and having this redundancy. We never really showed this before, and this is an example of being able to do that. You see, we're able to pretty much keep the end of the arm completely fixed in space, in position orientation. Right. But by moving this redundant axis, which is right along here, we can kind of reach it from a variety of different locations until it becomes kind of physically impossible, and then it's going to move around until it finds another point that it can go ahead and do it. So that's the idea of the redundancy that you have. Now, as far as like a robot task, if we want to go ahead and teach the very simple task here, and that is, I want this robot to come over and pick up this can and put it on over there. This is the traditional way of doing it. So we'll go ahead and say, I want to take this robot here, please, and I want to bring up this little program editor that allows me to see what's going on. Sure. And I physically have to start moving the robot around to get it over to where I want it to be. And if you're on the shop floor, you're going down there and you're eyeballing that. Right. If you are working in sort of like a simulation environment like we are, you're going to come around and you're going to ask it to find some sort of point on top of that geometry. You'll say that's good, and now you can teach a point. And up here in your program, you'll be able to say, okay, I stored that point. Right. And then the next thing you would do is that you can say, and actually I wanted to make that a linear move. And I'm going to just take that out for a second, because what I now want to do is sort of show it the approach point that I would like to have, because I can't go straight to the can. Otherwise, I'm going to knock it over. So you're already thinking ahead. Oh, what's the robot going to be doing? And I'm going to put that in there. And I'm actually going to put a second one in here and change the order of these. And the whole idea is that as I go here, I come on down. And after I grab it, I move it up. But you see, oh, I didn't actually grab it. I'm going to do something about that. So you've got to remember to give this instruction to go ahead and grab. Right. And that will and I'm assuming with a certain amount of force or a certain amount of closure. Or there might be something built in. It might be as simple as a signal that you just go ahead and turn on. You say, when this signal goes on, just go ahead and do the grab. And then there's going to be some magic in the background that makes sure that it closes the right amount of distance and it doesn't have a crushing force and everything else in there. Right. So you go ahead and do something like that. And now if I've got my steps right, when I run the program, the robot goes over and grabs it. Okay. So now that I sort of have it grabbed, I can continue to say, oh, it would be really nice to bring it over here to the table, and then, bring it on down to the table somewhere. Okay, it looks about right there. Yeah. And then go ahead and teach another point right there. and that'll be like this point along there, and then similar kind of things here that we need to get a couple of points there and another one, and then move it around, and like a little bit of reorganization.
Right.
So you can see the tedium that's going on in here on what I have to do. And then, so once I get down there, that's going to be the release. Okay, so I've now taught that can.
Yay.
All right. And now,
but it's a lot of steps. And also, if
it'll do it again and again. Now, what happens if I go ahead and take this can and say, oh, this is a shorter can?
Right.
It's going to be like that size. So now I change the dimension of the can. The robot completely misses it.
Or if you just moved it a few millimeters out of the way or something like that.
Or move it, it's it's completely different size. And then of course, if it's really big, it won't know that necessarily because it's just playing the same thing over again. And that would just kind of result in us crushing the can and moving it on over.
Right.
So that's not exactly the way that we would like to teach it, but that's the traditional way it's done because the robot has no smarts. It's just able to replay those instructions exactly.
Right.
Now, the other way is to go in and to do something which is going to be more task-based.
Right.
So rather than my going in and teaching the points, I would like to say there is something we would like to have happen, and that is whenever a can appears here, I want you to just bring it on over there. And that's where you start doing something with some kind of process editor, where you would say something like, oh, what I'd like to do is using this robot here as a resource. I would like to, and I'll just remove that because that was there before, is that I would like you to say, go from here over to there. So I want you to move whatever is here over to there. And that's all you have to do to program it.
Cool. Now, is it using the same code as before?
It's generating a lot of the code in the background. So
okay.
What I can do is that if I turn this thing on and I think I'll go ahead and get my robot positions, we are going to see that there should be some points appearing as we go along here in space. Right. If I've got them turned on right here. Okay. You're going to see this P1 jumping around.
Yeah.
Basically, we're calculating that because in a sense, we're omnipotent in the simulation world. We know where everything is. We know its position, its size, what it is. And this is something that you would do with an AI labeler. The first thing you do is that you label all these things. So now that you know what it is, you can start thinking about, oh, what's the best way to grab it? So in this case, we can make things a little bit more fancy. I could go ahead and say, let's go ahead and take this feeder, and I want to change something about it. Is I want it to do a distribution pattern where I've got two different size cans coming in, just randomly, and now randomly adapt to it. So if it's a tall or short, it'll just go ahead and figure it out. So we go ahead and run this. Okay, now when it's tall, it automatically adapts. So and the other thing we could do is we could do something like go ahead and take this and move it to a new location, and then it should adapt because you now know it's over there. So that's the difference between something where you're doing point-to-point programming and something where it's more task-based, where you're able to identify where positions are in space. Now, you would need some system to track where these things are, either a vision-based system or something else that identifies that, hey, I'm over here.
Yeah, I was thinking about that. I mean, since it has no vision system, it's pretty much you have to tell it that the table's moved over there at that point.
In this case. In this case. And so when we're doing simulations, we're trying to do proof of concepts to see what things are going to look like, whether it can be reached, what a cycle time would be. And there's other things you can do in this. You can specify what's the approach distance. So do we want to be 25 millimeters above or 100 millimeters above when we grab it? How much do we want to retract when we come up? So those are all parametric properties you can put in there to make things go a lot faster so you don't have to do it. So that's the idea of task-based. And that task-based stuff could be turned into a language. Where you could start just typing in some very simple instructions, say, I want you to do this, that, or something else, and it would figure it out. And then you would need some sort of language-based parser to go through and break it down into those individual instructions.
Right. So the from where we are here, we need a vision system, apparently a LiDAR system so it can actually project into 3D space and know where objects
Yep.
are, which does actually, you know, for robots, I know Tesla doesn't need this because they have their awesome vision system, but for the most of the rest of the world, having a LiDAR system is a good idea. But that way it's able to see where the Coke can is, for example. It's able to actually model that out in three-dimensional space. And then you also need a in this case, this is a task-based system that's pretty much all hard-coded, right? I mean, it's just a lot of very clever coding. So in the case,
it's actually a lot of very good Python scripting.
Yeah, yeah.
So to automate what we were sort of already doing over here, because you notice what I was doing was going through the same steps again and again and again. You're like, well, why can't I script that?
Right.
So
exactly.
That's what we're doing. Yes.
Yeah. Yeah. So, but in the case of Google, it's actually I would assume that they're using neural networks since they're attaching this to natural language processing. Right. So they're working hard on, okay.
Right. And they have a lot of things. I think they point out in one of the videos, you know, trying to identify the bottle. You know, this is something we should all understand. So what number am I showing you right now?
Number 9 or G, depending on what you're looking at. So,
or maybe it was actually number 6.
Could be a 6. Yeah, that's true. Orientation wise,
and this is always a problem with character recognition, is you never know based on its orientation exactly what it is. And that's the same thing they were talking about the bottles. It's like it's like, oh, this is a bottle. Oh, what's that?
Right.
It's a bottle lying down. What's this? And computers have a problem with it. If you look at like a QR code, for example, you notice the 3 corners of the QR code. What are they there for?
I'm sure it's for orientation, so it knows.
It's for orientation. And of course, if you remember, you know, a lot of times you do something like this to say, this is a 9, even though you see it like that. That's supposed to be down there, so you know it's a 9. So there's something to kind of orient it. So that's already a problem. Is that you're identifying these things in different positions and orientation, which is already a challenge. Right. And then, you know, is it a bottle? Is it a can? Is it made out of glass? You can see all sorts of different properties that are going to be very tricky to be able to figure out. Right.
Yeah, and that makes a really big difference. So, but you know, so it's got to be able to see it. It's got to be able to recognize it, identify what it is, and then I think the other part was that sort of breaking it down into small steps, which is kind of along the lines of what you were showing in your simulation. It's like once it sort of knows where it is and what it needs to do, then it's like, what 5 steps or 20 steps or 50 steps do I need to do to make this happen?
The simple thing is, I say, John, bake a cake for me. Right. Okay.
There's a lot of steps involved.
There's a lot of steps. Okay. So that now you have to break it down in your mind. Well, first I need to you know, find out what are the ingredients. Do I have the ingredients? Do I have to go to the store to buy the ingredients? All that. And then go through the procedures, everything else, and break it down. And that's exactly what we're doing there. We're saying, all right, pick up the Coke can. Right. And you know, there's a series of steps you have to go through to go over it and get it and bring it on up. I wish there was a lot of things we could do a lot faster. Like whenever I'm doing a simulation and a client is describing to me what the simulation has to be, right, within like a minute, I know exactly what I have to do, but it takes me a week to do it. Right. You know, because there's all these little steps you have to go through. And I wish there was just some way I could spit it out to an AI and say, oh, okay, just do it. And it would figure out the same thing. But
I mean, that's obviously the goal of what they're working on here, which is, I think the example is I spilled my orange soda, please clean it up and go to the fridge and bring me a Coke. And it's like, there's a whole bunch of steps involved. It has to go find the mop, has to find some water, has to put the mop in the water, has to, you know, find the spot where you spilled it, pick up the old soda can, put that in the recycling bin, mop up the mess, then go to the refrigerator, find a Coke. Hopefully there's one in there. If not, you may have to go someplace else. You know, so this, when you start breaking it down, there's even a very simple task has many, many steps in it. So
yes. Yeah. And I think in one of the videos, they even show the robot putting something in the microwave. It might've been like popcorn. Right. And I wonder if it knows that when you put popcorn in, you hit the popcorn button, or if it knows the right time, or if it picks up just some sort of item, whether it's scanning it or reading it to find out how long it's going to take to cook it. Right.
And that's an interesting question, because
internet search.
One of the things, I don't think this has ears, and what I generally do when I cook those microwave popcorn things is listen. And when it gets to more than about a second per pop, you stop it. That's about the ideal
That's
time.
yeah, that's the other trick. Well, that brings up the other thing is it seems like the instructions are text-based. Is that correct?
Well, I mean, you're saying it to the robot, but I believe it's translating that into
Okay, so it was
understanding. Yes.
So I wasn't sure if I was seeing spots. Yeah, I guess they would probably be saying it, and then you do the speech to text conversion,
right?
And then the text gets compiled. Or
yeah, I could be wrong about that, but I mean, Google's got that technology already. They've got their little Google, whatever's,
yeah,
those things, the Hey Google thing. So clearly that part can just be stuck in on a front end, and it can spit out text. So, but then the text has to go through some sort of natural language processor so that it can actually understand what the heck it is that you're talking to it about.
Right, because what you say may not be syntactically correct.
Right. Well, you think differently.
Sort of,
yeah, like a human being, when we talk to each other, we do not talk like we're programming Python.
Yes.
We're not that. You have to be very, very exact, and everything has to be in its place, or else you get a syntax error. Whereas humans are much more flexible about the way that we talk to each other. So, so a robot that's actually going to interact with humans has to become much more flexible about that.
Yeah, I agree. Now, they also mentioned in there that they do a lot of simulation. I think there was a glimpse in one of those that they were showing that these simulated worlds. And their feeling is that the only way they can get the robot to learn to actually to grab a bottle is to attempt to grab a bottle about 500,000 times before they get it right. And they're hoping to improve that, I think, from 500,000 attempts to maybe 500 or 5,000 attempts.
Right.
Which, I mean, it does seem like a long time for some of these tasks, but the idea is that by trial and error, it learns and learns and learns in an area that is very safe. It's very, I guess you could say it's sort of child-proofed.
Right.
Can't fall down and skin its knees or anything like that. And then eventually they turn it loose in the real world. Now, I think the other decisions that they made with the robot is that because it's on wheels, it's designed to only operate on a flat surface and in a single-story building. Unless you have an elevator, it's not going to be working on different floors.
Right.
And they've kind of set it up to work kind of more in a lab space, which is where they're in. And I don't think it's really something they expect to turn loose in the world at large yet, because there's going to be a lot of challenges with mobility. However, there are many applications where that's more than good enough.
Right.
Absolutely good enough. You don't have to necessarily go downstairs or go outside the house or do anything else.
Right. Yeah, and especially in factory situations and things, most people, if they're working, are going to stay on. Even if there's multiple floors, you're probably not you're not running up and down stairs all the time. That would be incredibly inefficient. So you're probably working in a contained area on a single floor.
Hospital settings are pretty similar too. A lot of times you're just working on one floor, and there's always an elevator to let you go up and down.
Right.
And there are already service robots that do that are able to take the elevator down to the kitchen to pick up the meals and bring them up to different patients. So
actually, a robot that could deliver meals to patients in a hospital would have a great deal of utility.
They already exist.
Yeah,
they exist. They've been around for a while. So it's not that hard, and they have to go very, very slow.
Right.
Because you want to make sure you don't start creating more patients.
That's true. Well, I was thinking about that because, again, one of the things, DeGogo didn't really focus on that in the cold fusion, but he said it is slow. That's one of the problems. And so,
it has to be.
Yeah, well, I mean, partially it has to be, but also I think that they're just not that quick about, there's a lot of stuff that it has to figure out. So
yeah, that's what I wonder. Is I've noticed the same thing with full self-driving. Is it seems like it's ready to take the turn and it just hesitates. And I wonder is it hesitating or is it really just slow?
Right. That's an interesting question. I don't know. And actually, this morning with the left-hand turn thing, I did a video on that. And you've been doing battle. You've been battling the Ents, so I noticed
and the right turn, turn.
So it's interesting because there are places, which again I think explains why full self-driving is so darn nasty. Because all of these other things, if you need to go slow, you just go a little bit slower, no big deal. But you can't drive 10 miles an hour under the speed limit in a normal traffic situation without making everybody around you super irate. So,
yeah. And the thing with the cobot, which is really what that is, and it would fall under sort of the the requirements and specifications for a cobot is that when it's close to humans, it has to operate at a very slow speed range. If it realizes there's no one around there, it could go a little bit faster. But even then, its high end is going to be slow.
Right.
And you'll notice there's no sharp corners on that thing.
Right.
You know, you might say, oh, it's not aesthetically pleasing. Well, it's designed to be rounded and smooth like that for a reason.
Yeah.
It's just to make sure that there's nothing that's going to cause injury. And,
Sure.
and actually, when they were developing their cobotic standards, and in Germany and other places, there were actually student volunteers that would sit in the way and allow themselves to get hit with a robot, a cobot. And then they would be asked, does that hurt? Does it, you know, at some point, oh, that hurts a lot. And they're like, oh, okay, that's the standard right there. And then probably, yeah. And you also notice they have to get rid of pinch points.
Right.
The elbow that they have has to be designed that if something kind of gets caught in there, it's not going to get stuck and broken off very easily. That's why there's a lot of separation space in there.
Gotcha. That's interesting. And also I noticed the fact that it's very bottom heavy. So if you hit it, it's more than likely going to tip itself back up again because it's got most of its weight in the bottom part of its body.
Yeah.
So while we're talking about this, let me just, because I think this, can you see him?
Yes.
Okay, so let's talk about Optimus because he's not following any of these rules except for the soft part. It doesn't have any hard edges. But this is a more ambitious project specifically because it is doing a lot of the things at once. So it's walking, it's interacting with human beings in a potential, it doesn't have an automatic balance point at the bottom, right? Its center of gravity is going to be much higher, sort of probably around the stomach chest area. So it's much easier to tip over. It has multiple fingers, it has arms, it could actually have pinch points in terms of like, you know, I don't know what you would do, but if it did this and it closed its elbow, it could actually do something like that. Again, you know, this is over a year ago now, this prototype or this rendering. So it will be very interesting to see. Neither one of us has a clue what they're going to be showing us.
Right. So what Google did is said, wait a minute, we're not going to do the walking. The walking thing is hard. Let's just make a mobile platform for it.
Right.
The arm that they have is really big. If you think about it, that arm is much bigger than a human arm, but it has about the reach that you sort of be able to get from a human when you throw the torso in and everything else. So they intentionally made it really big. It's got one arm. The problem with one arm is there's a lot of tasks that you cannot do with one arm. And, you know, one of those tasks is carrying this box, you know.
There we go.
It's a bit tricky, you know, maybe with their gripper, if you've got a grip point or something like that.
Right.
That's a bit different. However, they did show some examples of two of their robots cooperating together.
Right.
To give you kind of the two arms. So that might be one of the things they're trying to do. And I think they were trying to like fold sheets or something like that, which I always thought was like a four-arm process, not a two-arm.
I think we human beings fail at folding sheets because we don't have enough arms. I use my head, my legs.
It's a very different approach, but you know, they've decided we are going to put the AI chip or whatever it is that they're using into the body of a robot, and we're not going to worry about what the robot looks like.
Right.
And we want it to operate in a real-world environment, so we have to make sure it's extremely safe. So what we're just going to do is take off-the-shelf technologies, not invent anything new, so we can move rapidly on that.
Right.
Tesla is trying to do two challenging things at the same time. Okay. Now, that's not unlike Elon to try to do three or four very difficult things all at the same time.
And I think I would actually throw in a third. They're not using radar and LiDAR. They're using only vision.
Pure vision.
So they do have that problem solved to a large extent with full self-driving. Whether or not, there's a lot of people who are like, they're still going to need radar for like snow and rain and things like that. Whether or not you argue that for a robot in an interior situation, it's never going to, I really hope it's never snowing or raining inside the building. So, you know, so vision will be completely adequate for a robot like this.
And it's a lot slower. It's not going at 60 miles an hour.
Exactly.
It's only going at 5.
All right. So in terms of the way that they're approaching this, who's making the right decision, Google or Tesla?
Well, I think of Google as not being a hardware company, is being a software company.
Yeah.
And so their decision is that we want to get the software up and rolling right away. And I think that was a smart thing, because if halfway through they find out, oh, we're having all sorts of snags with the hardware, we can't do this and that. I mean, just I mean, look at the whole Artemis project. We're not going to get to the moon on time because the spacesuits won't be ready. You're like, you've got to be kidding me. So I mean, that's the whole idea that some stupid little thing can be a snag when all these pieces have to come together.
Right.
So they just decided, look, all this technology over here, we know it works.
Yeah.
It's been working and working and working. There's not going to be an issue. Let's just go ahead and bring it in there and just see what happens when you start to put an AI brain in there. So there's nothing wrong with that. Yeah.
Okay. But because Tesla has the manufacturing prowess, you think both are viable ways to go, I guess, paths.
Yeah, I mean, I think it's a good idea to go ahead and try to do that, and not to try to solve something like, the walking problem. And by the way, you should have Gary Snyder on the show sometime, who is someone I met who knows a lot about physiology. Actually, he runs a motion capture lab out in Denver, and he has some really intriguing insights on how walking works. And he says that Boston Dynamics, they've really figured it out, because the way their robot is walking, he says, is a lot closer to the way humans do it, and people who are very adept and very good at walking or running. And so it'd be interesting to hear his insights on what the challenges are to being able to make a humanoid robot based on his knowledge as being a physiologist and knows a lot about the inner workings. So that would be something interesting. Yeah.
Yeah, because human anatomy, of course, is not nearly as simplistic as we make it.
Yes.
We think, like just ball joint.
Actually, when he comes on, you're going to learn a new part about the human anatomy that you never knew about before, that I had never heard of either. Okay. That I'll keep kind of as a little surprise for everyone, because you're like, really? I didn't even know that exists. I said, yeah, most doctors don't even know it exists. It's critical to how the whole thing works.
Wow, that's crazy.
Yeah.
Man, well, I don't know. So reasonably, Google not being a specific hardware company, it makes sense for them to do simpler hardware, just focus on the software. Tesla being a hardware and software company, it makes sense for them to focus on both.
Right.
Is there a winner in this? Are there room for both of these types of robots in the world?
Oh, well, I would think so. I mean, the question is what's Google's long-term aim? Is it to put in everyone's house, which I think they sort of allude to on their website, that they would like to be able to do that. Teslabot is sort of seeing that it could do that, but right away they're saying we have a problem in the factory and we think we can solve it with robotics. Right. So they each are going after, I think, a completely different problem that will satisfy their needs. And which may explain why Tesla had to really go into designing the hardware, because it wasn't so much about the AI.
Right.
Part of it is that, but the other thing is like, but we need to be able to have something that can actually function in our factory. And to do that, you have to have a human form factor.
Right.
So that probably dictated a lot, but they definitely bit off a lot. And I will say it again, the prototype will be hard. The manufacturing will be easy when it comes in.
It's going to flip Elon's thing on its head.
Yeah, because again, I mean, even look at what Google did, is they went the simplest gripper possible.
Right.
They're just like, no, we're not going to go with those fancy hands. And I've mentioned this, the Fermi paradox of robotic hands. Where are they? Exactly. I've seen, these pictures of them out there, but I have not seen them in practice yet. So there seems to be something very difficult about getting them out of the lab and actually into manufacturing.
Right.
To daily usage.
And actually at the beginning, when I was rewinding and I rewound too far and it showed the OpenAI when it was solving the Rubik's Cube, that was just a hand sticking out of a wall. So there's probably a whole bunch of machinery behind that wall. So fitting that into a guess I must have hurt myself climbing today. But but like this whole thing, fitting it into a tiny little arm is complicated. That's really, really difficult.
I agree. I agree. The interface between the two seems to be a lot harder than you would think. I thought it would just be, just pop that on the end of an industrial robot arm and we have it, right? No, it's not there yet.
So interesting. All right. So any final thoughts? I think this is just a fascinating way to look. What Tesla's doing is not the only avenue possible. In fact, it's the hardest avenue possible, because they're trying to solve everything all at once.
Right.
Whereas Boston Dynamics is solving mostly the balance problem and the motion problem, and then you've got Google,
not the AI.
Right, without the AI, and Google solving mostly the AI problem, and then you've got Tesla that's kind of saying like, we're going to do both.
And of course, the funny thing is Boston Dynamics used to be owned by Google.
Yeah, that's right. I forgot about that.
They own them, and they should. And who knows, maybe eventually they'll come back together if they get the AI part kind of going. Yeah.
Right.
Yeah.
So that is a big advantage for them. All right.
Yeah.
Well, thank you so much. This was a really, really fascinating chat, and I hope people learned a lot. And this is just a way to get hyped up because we are 12 days away from AI Day. I believe that's correct.
Yeah.
So September
close.
30th. Yeah. I guess it'll be 11 days away by the time this comes out. So anyway, September 30th. And it will be utterly fascinating to see whether it's going to be a pile of wires with a hand sticking up out of it that does something, or some sort of semi-polished robot, or who the heck knows what it's going to be.
I don't know. No one has said very much. So we're not hearing much whether hope should be high or whether it's just going to be some videos of it doing some cool things in the lab, and whether they actually would want to bring it out for a full display in public. I guess the last thing to say is that normally we talk about the T-shirt. So this time I think I've got a math T-shirt that I don't even think Mythologer has. It was a gift from some friends who I will be seeing this week, so they know who they are. But yeah, it's all the different functions, as you can see, and how moving your hands around to get them. So all the math
gets a little complicated after a while. I've just got a boring one on. I've just got this Teton bouldering project that I got years ago in Jackson, Wyoming. So I figured like you can never really see when I'm talking, so I'm like, it's not worth wearing a cool shirt. But now you called me out, so I have to show it. I like yours better. Yours is a better shirt.
Yeah, so you gotta keep it in mind. But you do way more episodes than I do, so my T-shirt collection doesn't have to be that big.
There you go. All right, thank you so much, and everybody. I hope you all appreciate Scott spending time with us and talking about this. You're quite the authority on this stuff, and I really appreciate, especially like getting to see the robots in the simulation. That was really, really cool. So thank you all so much. Thank you so much. Sorry, and everybody, like, subscribe, do all that good stuff, and we'll see you later. Bye-bye.
Cheers. Do you know what the Scara robot looks like?
I'm not sure.
Okay, then let me quickly do that, and we'll go ahead and show you what it is. So this was the inverse kinematics we wanted to work on here. Let's see. Let's go ahead and get that ECAT up here, and let's go ahead and find a Scara type of robot. So this is one of those that's very easy to do. It's something that we pretty much have.
Okay, yeah.
Yes,
it's like a tabletop kind of.
It's a 4-axis robot. It's very easy to solve. It's one of the first things that everyone can solve in their class of robotics.
Right.
Because it's very similar to polar coordinates. Very, very, very similar in that pretty much what you're doing is that instead of having that translational arm for changing the radius, you use these two rotational arms to do that for you.
Right.
Right?
Yeah.
So just think about the polar coordinate problem. And
you just move the origin over and you solve the polar coordinates twice and you're done.
Yeah. So rather than having a translational here, and basically it's a cylindrical robot, because polar coordinates and cylindrical coordinates is like, well, the Z just make it go up and down and turn into a cylinder. It's very easy. So if we know the distance from here to there is supposed to be like somewhere in the middle, then we do this with the elbow to get that. And of course, what we have to do is that we have to compensate for the fact that when we move this one, it sort of misses its target. So the first axis has to kind of come over and compensate for it.
Right.
And then the height, well, it's just making this thing go up and down.
Right.
And then if you want to throw in the orientation, you can just do this.
So you have only one orientation. 4 axes. Okay, gotcha.
Right. That's where you get the fourth axis. And this one is very easy because basically the rotation of these things here kind of cause that thing to rotate. And then you just counter whatever rotation you have here, you take it out.
Right.
So if you want to think of the flow chart for solving that, looks like this. These are your inputs, your X, Y, Z, and W, which is the rotation that you have to do about the Z axis.
Okay.
And the Z is almost straight through to like your third axis.
Right.
And so it's like, it might be that you define positive direction for the Z this way. Whoop, but the robot thinks positive is the quill is going down that way. So it's like, okay, a flip and some offset. So you can imagine that's pretty simple. And that looks like exactly what you do at one of your nodes anyways, right? That's basically a neural network to do that.
Yeah.
Yeah, that's just a multiplication, I guess a scale plus an offset.
Yeah.
Right. And then the X and the Y, they get a bit trickier. So I could see these as almost like the hidden layers.
Yeah.
That X and Y have to combine together to get you J1 and J2.
Right.
So you can't get J1 without knowing X and Y. And vice versa. And we could see there's like a couple little steps they kind of go through that. I could almost imagine this is like a subneural network that understands square roots, and another one that understands the law of cosines.
Right.
Which both of these are basically the law of cosines. With some other things. So they kind of come through, and that gives you J1 and J2. And then the W, like I said, is really pretty easy. It's just once you know J1 and J2, you just subtract those off of it, and that's J4. So again, this is almost as easy as that. So I could see that this solution should give us these Z and W almost precise. Well, W maybe not precisely, because if it doesn't get J1 and J2 right, it screws up. But you see the analytical solution is pretty simple. Now, I'm only going for one solution here. I'm not doing the plus or minus here on the R.
Right.
So I would be satisfied to say it just gives us one solution. Or basically, the data points that I gave you are just with the elbow positive the whole time.
Right.
So it's only going to come up with that one solution. And then what you would do is we would teach it with the other configuration to get the second one. And then you would more or less say, oh, use this network or use network, or, there's two. So you look at the two solutions, and then you decide between the two solutions, which one is the best solution right now. And then the only other wild card is this is basically 4 in and 4 out, but there's kind of a fifth thing that should come out, and that is a warning that it's unreachable.
Right.
So in other words, the neural network would have to know that you've given it a combination of numbers here that doesn't make any sense.
Right.
But the way we're teaching it with reverse propagation doesn't make sense, because there's never a set of J values that's impossible. This set over here, those are always correct values that go backwards to give you these.
Right.
The thing is, I can give you X, Y's, and Z's, which are invalid. But it's kind of because we're teaching it with reverse propagation. I don't know how we teach it that it's bad.
I mean, again, what you would do is you would give it possible. You have to think about this backwards a little bit. You would give it a whole scatter plot of possible solutions, and
then a whole scatter of bad ones, X, Y, Z's that are bad.
Yeah, where it's just like it can't reach that far, or it's upside down, or something like that.
And that's very simple. That it's just like it's greater than its radius. It's like,
exactly.
X and Y are just combined.
Exactly, but you would give it some of those examples too.
So you would give it counter examples. Okay.
Yeah, you'd give it a thing where with a proper response was can't do this or something like that, right? So which was basically what they were talking about with the Google robot. They were saying that you have to teach it. So one simple thing would be like, it can't reach further than its arm unless it moves itself towards that thing or something like that. Or it can't reach up above however tall it is, So those kind of things grounded in a reality so that it knows what it's allowed to do.
Yes, exactly. Yeah. Exactly. So, just your thoughts looking at that. So that's what I think the hidden layers are going to look like. The neural network should look like that to me.
Right. Yeah, in a way, actually, that kind of models out a neural network really well. You have your inputs, your outputs, and sometimes
it's just that this thing here is weird. I mean, to me, it seems like, there's going to be a whole lot of other stuff going on in here, in here, and here. But I know this one is simple. That's that.
Right. Yeah, but you know what's interesting is you don't have to tell the neural network that whole arc cosine thing or anything like that.
Yeah.
You just feed it 100,000 data points, and it will literally figure out the arc cosine function.
And see, so and that's the thing.
It will figure it out.
I think will be interesting.
It's pretty crazy.
Is there some way for us to see what the hidden layers look like when this is all done?
Oh yeah.
Because this is my prediction of what it should look like. And what I would almost think is like, well, it's going to be one of these things where there's like something really strong in here, and then there's going to be this really weird looking web in here.
Right.
You know, but I don't know how you would be able to see that that's the weird web, and that these are much thicker lines versus what's going on in here. But I think that would be interesting to be able to see if our prediction of what it should look like turns out to be that way, or if it's just completely different.
The fascinating thing about this is that the X and Y are complicated and Z and W are very uncomplicated.
Yes.
So the way that neural networks are built, you would input 4 inputs, but the weights for Z and W would become very, very sparse.
Yes.
Most things would mostly just be like pass it on through, and maybe
the Z should just have 0 weights. Yeah. If there's a connection with anything over here, it's got it wrong.
Yeah.
It goes straight through. And again, the W is a bit weird because there's this dependency on the outputs.
Right.
That's it. But there's going to be something kind of weird in how that gets fed in there.
Right. So, but that is actually interesting. I don't know the way that neural networks work. They're sort of black boxes. So
I know that's why
who knows how it would actually.
The expert who would know, not me.
Well, I mean, let's. Do you have a way of generating a bunch of data points? I would assume you do. You can just run the simulation and have it.
Oh, I gave them to you.
Yeah, for that particular one, the Scara.
Yeah.
Oh, okay.
Yeah. That's what you have.
Well, then that'll give me possible points, which is fine.
Those are all the good points.
Yeah,
it's not the bad points, but let's not worry about the bad points right now. All I care is that it knows how to solve those, and we would give it the good ones, and they see what kind of comes out of it. But you should have that, and I'm not sure how many points I generated, but there were a bunch of random points.
Yeah, it should be enough. I mean, we should be looking at something that's along the lines of like, we could throw this at WECA or something like that. And I don't know. The interesting question, of course, would be how big of a neural network do you need to model this? Because that arc cosine plus arc tangent is a reasonably snarly function that it's going to have to learn. So it's going to have a few layers. Again, I don't know. Well, so you've got a square root and then a cosine. So I could see it needing to have something like 8 or 10 layers or something in order to figure this out. But
that's not much. Now,
I don't know. It's just
the weird thing is that this is one of those things. The discussions I've had with Gary, and man, you can just talk about philosophy and everything with him. Is that I've always felt that if you look at where ideas exist, do we need a universe for ideas to exist, or do they exist on some other plane?
Oh, do we have a platonic thing
the concept,
going on?
The concept of 1 + 1 = 2.
Right.
Do you need matter and energy for that to exist as a thought or an idea? And then if you really look at it, all math is nothing but addition. That's the only function you need for everything.
Right.
It's like, well, multiplication is based, and subtraction is just a different form of addition.
Right.
Multiplication, well, what is multiplication? It's just, a shortcut for doing lots of addition.
Right.
What's the exponent? Well, it's just a shortcut for doing lots of multiplication, which is a shortcut for lots of addition. And then we get the sum function, right? Well, what's, which is literally adding things up. What's the integral? Oh, that's really hard. I don't understand it. All that is adding up lots of stuff an infinite number of times. And so everything comes into it. And even when we have these complex functions like sines and cosines, there's always like the power series that you could throw on it, or Taylor series expansion, that you can turn that nasty looking inverse cosine into a series of addition. Well, what does a neural network do? Addition. That's basically, a lot of what's going on there. And all you're saying is that, I just need to have enough hidden layers, which is basically enough additions set up the same way that a Taylor series expansion would be for the arc cosine.
And who knows how it would solve it? It might solve it as a Taylor series expansion or something along those lines.
Yeah, and
that's
something like that.
As you work through this thing, you end up in a latent space, which would be some sort of conceptual understanding on the part of the neural network of what an arc cosine was, or what a square root was. I mean, the R equals the square root of x squared plus y squared is, you know, classic Pythagorean theorem. So it also would have to learn what the Pythagorean theorem was.
Yeah, it would learn that. And the other thing that's not in here as a parameter is like L1 and L2, but that's implicit in the data set that I gave you.
Right.
And then if we can get this thing to work, it would really be interesting to kind of somehow tease it out and say, all right, what we're now going to do is we're going to take scalar robots with different L1s and L2s.
Right.
And I'm going to give you the data set for that L1 and then for this one. And they're going to kind of be inputs going on in there. And then we see if it's able to learn how to do it for any scalar robot at that point.
Right. Well,
but
what you would have to input more data points, because in addition to just, so XYZW are the target point,
the goal,
right?
That's a target. Yes.
Yeah. So you had the input. So honestly, it would be, it's actually going to work in backwards. It'll actually flow backwards. You will give it, no, actually, I don't know. No, it needs to provide the, this is actually the right direction.
Yeah. So normally what we do is we think of those as hidden parameters in the function. So the function call is, call IK, XYZ, W, semicolon, L1, L2.
Right.
Those are the variable constants.
Yeah. But L1, L2 being, what are those?
The length of the arms. And they don't change. Okay. I mean, it's for that arm. So what we'd be saying is that we have a series of scalar robots where we do them with different arm lengths. So I have one set of arm lengths, and I give you all the training data for that.
Yeah, that's what I'm saying.
This is what L1 and L2 are. They're fixed.
Right.
And then we do it again, the same training, I guess almost the same set of data, except L1 and L2 are different.
But this is what I'm saying. What you would actually do is throw it all in a batch together. So you would give it XYZW, L1, L2.
Yep.
And then whatever the associated joint rotations were for that.
Yes.
And so the whole, so you
can do it all at once. You can do it all at once.
Gigantic data set, and that would figure out. So when you gave it the L1, L2, that's why I was trying to think about this, because the weird part is, well, no, you'd tell it how big the scalar robot was and where you wanted the point to end up. So so it would work. Yeah, it would work.
And then I guess the inverse would be that, okay, I want to reach this point, and the AI says, oh, you can't do it with an L1, L2s. May I suggest one?
Right.
But
that was what I was saying was, you could actually, if you did this right, you could train it to figure out to have the L1, L2 end up being part of the output. So you give it,
it's not reachable. Yes.
You give it XYZW, and it tells you what the optimal size scalar robot is. So, so that actually becomes part of the target, not part of the input.
For all actually for like,
right.
Ooh, yeah. That would be an interesting application. You're right. Is that to say, these are all the points I want to go to, now suggest the robot for me.
Yeah, exactly. So that certainly would be doable.
Oh, yeah, that'd be a really cool application. Yeah. The first thing we have to do is make sure the inverse kinematics can be done.
Right.
Yeah.
But it should be. The other thing is, of course, that what this would do is give you, like, L1 would be 27.14271 centimeters or something, and you're like, well, I don't have one that size. I have a 20 centimeter one.
It has to be discrete. I can only buy them in these sizes. Exactly. And a lot of times we do that. And